Hello, my name is Arabdha, and I'm going to be going over my project, which is heart disease prediction using a multitude of both machine learning and deep learning models. So first, a little bit about my data set. What this data set is it's a list of individuals who either have heart disease or don't have heart disease, along with a set of predictive values or values that we'll use to predict whether or not they have heart disease. And again, here's some information about the types of data we have, things like age, sex, resting heart rate, cholesterol levels, things like that. And in terms of the split in the data set of individuals with and without heart disease, there's a little bit biased towards individuals with heart disease, but it's pretty close and it's almost 50-50. So because of this, I thought that, using this data set was appropriate and there wouldn't be any bias towards, individuals with or without heart disease. And again, here's just some more information about the different types of data, just taking the mean group by target. And we can see that there is certain values are just much higher because of how they're measured or the units of measurement. And because of this, I'll be normalizing the data later. And over here is, again, just some values or some histograms plotted for each of the different, columns of the data frame. And we can see that a couple of these are clearly categorical values, such as thal, CA, and slope. And because of this, we convert these into dummy variables and use that in our model. And so the first model that I train is the K nearest neighbor model. And this first block right here is just using a naive number of neighbors of 14 and training that after splitting the data into a train and test split. And this returns an accuracy of about 83%. And then what I do here is I try to optimize the number of neighbors to see what that ideal number is and what the ideal accuracy is. And after doing that, we'll see that we reach that ideal accuracy a couple of times, and the lowest number of neighbors we can use to reach that almost 89% accuracy is 2. The next model that's trained is a random forest and a decision tree, which is, two similar things. The decision tree returns an accuracy of 77%, which is pretty low, while the random forest returns an accuracy of about 89%. And what we have here is the feature importance extracted from the random forest. And we can see that, certain features seem to be much more important in determining whether or not an individual has heart disease. And this is a little hard to see, but that's kind of the representation of what that decision tree looks like. And here's the feature importance of said decision tree. And next, a gradient boosting classifier is trained, which is in essence just a boosted decision tree. And it again only returns accuracy of about 80% on that training split. And again, that feature importance is extracted. And just to test it, a logistic regression model was fit just to see if, sort of the quote unquote simplest model, how that would perform. And it performed pretty well, returning an accuracy of about 86%. So next, what we're going to go into is using a couple different neural network architectures to train on this data. So the first one is just a simple neural network. And my goal here was to overtrain the model and get it to 100% or as close to that accuracy on the training data set. And, then adjust the model based on that. So we have two hidden layers with one sigmoid activation function layer at the very end. And with 21 inputs into the model, we use ReLU activation functions throughout. And the optimizer is Atom, and we have metrics being accuracy. And the loss function is binary cross entropy because the target is whether or not an individual has heart disease, with training on 200 epochs with a batch size of 10. And if we go down here, we'll see that the accuracy gets to about 99.45%. And when we use this on the actual data set, it is at 78%, which is really low, almost as low as our lowest current model, which is the decision tree. And if we look at the loss function between the test versus the train, you'll see that after a certain amount of time, that test loss function just increases rapidly and doesn't decrease at all. So to combat this, the first thing we did was, or that I did, was introduce early stopping. And after 5 epochs, after no improvement in the validation loss, the model should stop. And it stops at around 19 epochs, while the previous model was trained to about 200 or 300. And the accuracy here, sorry, ends up being 88.5%, which is significantly higher. And again, we can see the loss does tend to change a little bit, but it's obviously much closer than it was before. And finally, the last sort of model that was fit is using dropout layers after the hidden layers, where we're dropping about 20% of those nodes. And the accuracy here ends up being 85%. So it actually performs worse with dropout. And over here, we have a list of all the accuracies of all the different models. And, oh, sorry, that should have been after this, but these are again some graphs of that last neural network model where we see a similar difference, but a much messier training loss function. And as we can see, the accuracy gets to about 85% or so, or yeah. And then this is just sort of comparing the different models to see which one is best. The nearest neighbor, the random forest, and our second neural network model performed the best, all at about 89%, while the decision tree and that first neural network were the worst at about 77%. And yeah, that was my project. Thank you for listening.